Well, in this lecture, we are going to go through certain signal processing examples using MATLAB. Like in the previous class, you would have just seen an introduction to MATLAB. MATLAB is a very popular software amongst students in the universities, and those of you who are from the industry may not have ready access to MATLAB, but then you could also do the same logic in Excel. And we will. The idea behind this lecture is to help you understand some of the signal processing processes or techniques which we have discussed, and we will do them as we go in MATLAB, so that you get a feel of how the signals are generated and what kind of analysis is being done, particularly to find out their frequencies and so on. So, the very first example in MATLAB is just doing a sine wave time history. I will explain you this, and then we will go through this in MATLAB. So, basically what I have done, I have generated an index from 1 to 1000, that is the time steps. I am sampling the signal at 1000 hertz. So, the sampling interval is nothing but 1 by 1000, that many seconds. I have a signal of 10 hertz. By the way, when you see a colon or a semicolon, MATLAB ignores everything after the semicolon. So, anything in percentage is actually a comment statement, and such comments are given here for our understanding. So, for at any instance of n, the time is given as n times delta t. So, now if I plot y is equal to 10 sine 2 pi f t, it will plot, it will generate a 10 hertz sine wave of 10 units amplitude, and will plot it as a sine wave. Of course, you can give a label, x label, anything you give within quotes, time in seconds. Similarly, y label within quotes the amplitude. Okay. So, let me just work it out in MATLAB for you all. So, n is equal to 1. As I was telling you, a very good idea is to always clear everything before you do MATLAB. So, n is equal to 1 to, okay. My sampling frequency f s is 1 by 1000, is 1000. So, delta t is nothing but 1 divided by, good idea to f s. I will have a sine wave frequency of f is equal to 10, and then time at any instance t is n star del t. I will plot y is equal to 10.0 star sine 2.0 star pi star f star t, and before you execute this operations, you would see that all the variables are already defined, like pi is already defined in MATLAB, f is given, t has been calculated, and so on. So, now I can plot see this. I have generated a sine wave for a total duration of 1 second. Now, why is this 1? All of you, those who have done signal processing, will know that since my I do not see the cursor coming in here, but let me come here then. See, I have generated index till 1000, sampling frequency at 1000. So, my total time when delta t is 1 by 1000 and n is 1000, the maximum value is 1 second. and my sine wave is of 10 hertz frequency. So, the time period is 0.1. So, within a time of 1 second I would see 10 complete waveforms of the sine wave, and that is what I see in this plot here. Okay, you can see this. If I move my cursor here, okay, this is 10 complete waveforms I will see here on the MATLAB screen. So, this is one example which we did. Okay. Now, let me clear okay. So, nothing is there. I can always do a who's to see that nothing is there, memory is clear. Now, I will go to the next example, wherein to the same sine wave I have added a random noise. Everything else is same. I have added a random noise, and then I am going to plot the sine wave with a random noise. So, let me just quickly go through what we did. N is equal to 1. Okay. T is equal to n times del t, and then I will add y is equal to 10.0 star sine 2.0 star pi star f star t, and to this I am adding the random noise of this amplitude 10.0 star rand 1. Yeah, I have not defined f here, so I will make this f as so what I could do is, I have by while typing I had mixed the expression f, so I will give f is equal to 10.0 and then execute this command now. Okay. So, you see, because while typing I had missed f, it was not able to compute this expression. So, once I gave in the value f and recomputed it, it has taken in the value. So, now I can plot you see, earlier I had a very neat sine wave, but now to the sine wave a random noise has been added. So, you can see in MATLAB, in fact, many of the real signals which you will see will be having such signals. Now, with this, let us go to another command or another program, wherein I am generating a square wave, okay, by given this expression gen t, okay, wherein I am generating a square wave for 1 second durations, okay, sampled at 1000 hertz, okay, and 0.1 I am giving the duty cycle, and then UA is equal to 10. So, you can always do help gen sing, just to be clear. Let me clear all here. Generate signal. So, generate signal type, you can generate tau, scalar signal u of signal type, and period tau. Okay. So, ut for the time duration of the signal and spacing Ts of the time samples in t seconds. So, let us do it like this, clear all, second bracket u comma t is equal to generate sig square 0.1 1 0.01. Okay. Now I am amplifying that amplitude by a unit of 10. And I will plot. Of course, I have to generate t. T is equal to 1. So plot t and still done some mistake here. Let me I can always do a debugging online whose UA T. Okay, I can generate this T is equal to T transpose plot T and K. Let me do whose 1001. Okay, T is equal to, let me, T is equal to 1. Okay, plot, sorry, T is equal to T transpose plot T UA. Okay. You see, I have generated a square wave. There is an error because I could quickly debug it. For some reason, UA is 1001 points, and initially I generated till 1000 points. That is why I get this error. Vectors must be the same length. So what I did is I increased T from 1:1 till 1001, and then made it transpose, and I plotted it. So I have generated a square wave. Okay, I will now go to the next example. I will clear all. So I am now generating an amplitude modulated waveform. You all are now familiar with the n sampling frequency delta t. Frequency of the signal is 10 hertz. So frequency, modulated frequency is 10 hertz, and the carrier frequency is 100 hertz. So I am generating a modulated sine wave, and let us see how it looks like. So quickly, if I copy whatever is given here, so n is equal to 1 to 1000, Fs is equal to 1000, delta t is nothing but 1.0 by Fs. F is equal to 10.0, the modulated frequency. Fc is 100.0, the carrier frequency. T is equal to n star del t. Okay. And then I will generate y is equal to 10.0 star sine 2.0 star pi star f star t, and you see this dot star sine 2.0 star pi star f c star t. Okay, I did a typo here. I can see here. This should not do in the second bracket. So I can correct it by, instead of pi, this should have been pi. Okay. So, you can see in real time we can do such corrections. So, my amplitude modulated signal is there. So, I can now plot t and y. So, you can see modulations of the amplitude occurring. There is an increasing, decreasing, again increasing, and so on. So, within a period of 1 second, or no, I have got the time. Okay, 1 second total time. It is a 10 hertz sine wave, which is getting modulated by a carrier frequency of 100 hertz, is how this is going to look like. Now, I will go to the next example. Similarly, for the frequency modulated signal, I will not do this in MATLAB here, but you can see the same sequence have been followed. Only thing is that when I have the frequency modulation expressions, similarly I have to change the frequency contained by this expression. Okay. And this could be one of your homeworks, to plot a frequency modulated signal in MATLAB. Similarly, I can generate a beat signal, okay, wherein I can we will see this beat signal when we do the case of heterodyning, where I have 10,000 points. The only catch in beat signal is the frequencies f1 and f2 are very close to each other. One is 10 hertz and another is 11 hertz, and I am just adding two signals, one being 10 hertz, another being 11 hertz. They will look something very close to an amplitude modulated signal, but they are not amplitude modulated in that sense. Now, I will come to one of the very important examples, as in how do I do Fourier transform of a signal. Okay. So, let us see this example here. So, before let me explain you what this is. You all are now familiar with this index n is equal to 1 to 1000, sampling frequency is 1000 hertz. So, delta t is the sampling interval is nothing but 1 by sampling frequency. I have a frequency of 77 hertz, okay, and total time of the signal is 1000 times delta t. So, I have generated my sine wave time signal of 77 hertz by this expression y is equal to 10 star sine 2 pi f t, and this is the most important command here, wherein I am doing the complex FFT of this 77 hertz sine wave signal, wherein you see this is a scaling factor which we use to get the right amplitudes. This is 2 divided by the number of data points. In our case, the data points being 1000, I will multiply the scaling factor with the FFT. But as you know, once we convert a signal from time domain to frequency domain, it becomes a complex quantity. So, YFFT is actually a complex quantity, which I will just calculate and show you. And then to find out the magnitude, I just do the Y abs of the magnitude, absolute value of the complex values of FFT, and the delta frequency in the frequency resolution in the frequency domain is 1 by total time. Total time is given by this expression here, and since the FFT results are plotted till n by 2 because of the negative frequency. So, I am plotting from 1 by 5000. So, I can plot at any frequency till n by 2 the del f, and I will slot this. Let us work this example out for everybody's benefit. So, n is equal to 1 colon 1 1000. Then I have Fs is 1000. See, it did, because I did not give the colon semicolon, it did not prompt me. Okay. Delta t is nothing but 1 divided by Fs. F is 77 hertz, that is the frequency of my sine wave. Total time is nothing but n times del t. any instance t. Okay. Total time is 1000 times del t. So, y is equal to 10.0 star sine 2.0 star pi star f star t. They are all been defined beforehand. So, now I do the FFT. Y FFT is equal to, this is very important. You may not find them in the MATLAB handouts. FFT y. So, the absolute value y abs is nothing but a abs FFT, and then I will plot the del f. Del f is nothing but 1.0 divided by total time, and then n2 is nothing but a new index till 500 points. Just to plot the first half, frequency at any instance of n2 is nothing but this times, sorry, is equal to del f times n2. So, now I will plot f k and y abs the first 500. Oh, okay. I made a mistake here. This should have been colon instead of a semicolon. So, I will correct it by putting a semicolon. It is good to do such mistakes, so that you get to feel. Now, this is the frequency spectrum of the signal. This is in frequency domain. I had sampled at 1000 hertz. So, this is till 500 hertz, and my magnitude is 10 hertz, and this is close to 77. Okay. So, let me explain you how we did FFT and what are the time blocks. So, to begin with, I generated a sine wave of amplitude 10. This at frequency is 77 hertz, where my sampling frequency was 1000 hertz. So, delta t is nothing but 1 by Fs. So, at every 2 points, this is my delta t. Okay. And this I took for n is equal to 1000, and this was only for total time was 1 second. Okay. Now, once I went to FFT, I plotted till 500 hertz. Okay, and the spacing just for this is your delta f. So, delta f is nothing but 1 by total time. In this case, because this is 1 second, our delta f is 1 hertz. So, since the signal was 77, at 77 hertz, I see a peak of 10 hertz, and this is what. So, this is in time domain, and this is in frequency domain. Okay. So, the relationship between delta f and total time is very important in this, and you know how total time is related to. So, total time is nothing but n times delta t, where n is the number of data points. Of course, I have not talked regarding windowing etc. No, that is for a later course, but this is something which we need to understand in terms of the frequency content. Okay. Now, I will move to the next. So, you can do an envelope detection, because whenever we have the case of amplitude modulated signal. So, this is an amplitude modulated signal here. Okay. So, I will just do an Hilbert transform of this signal, and then absolute value of the Hilbert transform actually gives the envelope of that signal. Okay. And similarly, like I was telling you, there are many features in a signal. Okay. So, if a signal has been generated, is the 5 hertz has been a DC offset added to a signal of 10 hertz. Okay. I can find out certain parameters, the maximum value, minimum value, mean, variance, standard deviation, kurtosis, skewness. These are all built-in functions in MATLAB, okay, which could be used to calculate these expressions. Okay. And then you will see the actual expressions for this in my book. Okay. And similarly, another example which all of you could try is the substrum analysis. So, I have generated the signal, I have then I have added certain sample length, okay, and where the sine wave is delayed by 0.1 seconds, and then I can see the complex substrum by this command here, and I can plot the Q frequencies at 0.1 second and its raw harmonics. So, this is very important technique of substrums. So, complex substrums is given by the C-subs command. Okay. So, some of these examples which we discussed in this are given in my book in an appendix. So, all of you could perhaps try it out on your own using MATLAB. So, with this examples, you got a feeling of how MATLAB could be used for signal processing, and then of course, later on I will showing you how such signals can be physically generated and what kind of signals machines give out, and what kind of analysis we can do either through a dedicated frequency analyzer or through a software like MATLAB. Okay. Thank you.